Let's have a look at this question dealing with dynamics. A massless spring with force constant K is attached at its left end to a wall as shown above. Initially, block A and block B, each of mass m, are at rest on a frictionless surface. We understand that the initial velocity u for block A is equal to 0. The initial velocity u for block B is also assumed to be 0. Now block A is contact with a spring and block B is at a distance of x from block A. Block A is then moved to the left, compressing the spring by a distance d. Now here d is assumed to be the compression length of the spring. And when the spring compresses, the elastic potential energy of the spring, or the energy stored in the spring, is given by the expression energy in the spring is equivalent to half the spring constant, which is given by the small letter k, into d square. Here the spring constant k is denoted by the small letter k. Moving ahead, we understand that when block A is released, the entire energy of the spring is converted to or transferred to the kinetic energy of the body A. And obviously body A will collide with body B as shown. And the collision is a perfectly inelastic collision. The keyword perfectly inelastic tells us that the two bodies stick together after collision, and the word inelastic also specifies that energy is not conserved during this collision while momentum is. And they follow a curved path. The curved path for the valley and the hill both have a radius r. We also need to keep in mind that when a body undergoes curved motion, or circular motion to be specific, it also has centripetal force, which acts as the resultant force, keeping the body in circular motion. Moving on, answer the following in terms of capital M, small k, d, x, small g, and capital R. Question A asks us to determine the speed of the block just before it collides with block B. The speed of the block can be found out by equating the energy of the spring to the kinetic energy of body A, which is equal to half capital M into V square. Simplifying the two expressions equated, we get the value of V to be equal to d root small k divided by capital M. This answers part A of our question. Moving ahead, determine the speed of the block just after the collision occurs. To determine the speed of the block just after the collision occurs, we just have to equate the change in momentum before the collision and after the collision. We know that momentum is conserved in this collision, specifically because it is said to be inelastic, and we find out that the expression can be written as MA into UA plus MB into UB is equal to the bodies sticking together, hence the combined mass is MA plus MB into the final velocity V becomes VAB. Here UA is no longer 0, and instead assume the value. UA is nothing but the value of V found out, which is d root k by capital M. When we substitute the values of MA and MB as capital M, UA and UB as stated, we get the final expression for VAB simplified to be equal to d divided by 2 root k divided by capital M. Moving on to part C of the question, we are asked to determine the change in kinetic energy for the collision. To find the change in kinetic energy of the collision, we use the expression change in kinetic energy delta Ke is equal to K2 minus K1. K2 is the total energy after the collision, which is half into the combined mass 2m into VAB the whole square minus the initial kinetic energy, which is just that of mass A, because mass B was at rest. And this value is equal to half into capital M into V square, where V is the value of velocity obtained in part A. Simplifying this further, we get the change in kinetic energy to be equal to the expression negative d square k by 4. Negative d square k divided by 4. Moving on to part D of the answer, we are asked to find the normal force on the boxes when they are at position P. Here, when we look at the boxes or the combined mass of the two boxes at position P, we understand that they are executing circular motion, which means they have a resultant force that is facing downwards. And also, there is another force facing downwards, which is the combined weight, while the normal force or the reaction force faces upwards. Since in part D, the resultant force is nothing but the centripetal force, which is equal to the weight acting downwards minus the normal reaction acting upwards, because it is in the opposite direction. We write the equation for N as N is equal to W minus F centripetal. Weight is nothing but mass times acceleration due to gravity. Here the combined mass is 2m times acceleration due to gravity g. This is subtracted from the expression for centripetal force, which is generally written as m into v square over 4. Substituted here as mass is 2m into v square is the combined velocity, because they are at the same height after passing through the valley, VAB the whole square, which was derived in part 2 of the solution, divided by the radius capital R. And when simplified with all substitutions, we get the final equation for N to be equal to 2mg 2 times capital M times capital G minus d square k over 2r.